Today is the second episode on our series on asthma, and I want to start this episode with a particularly interesting story, and it begins on a dark and stormy night. Lightning, cue thunder. There it is. I think it sounds good, right? So, I don't know if any of that happened. I don't know what the weather was like when Dr. Otto Loewi did a really groundbreaking experiment that really changed our understanding in both human physiology and in medicine. So a little bit about Dr. Otto Loewi to begin the episode. He was a German physician, as I mentioned. He wanted to be an art history major, but his dad forced him to be a physician. Apparently, he skipped a lot of medical school classes for lectures on humanities and painting. So much so that he almost didn't graduate. He had to do an extra year of remediation to complete his medical degree in 1896. But he finally graduated and became interested in human physiology, particularly the nervous system. Around this time, there was a great debate. How do nerves communicate with one another? At the time, one field of thought was that nerves communicated via electrical sparks sent from one synapse to another, right? This sort of makes sense. We know nerves communicate very rapidly, and electricity is quite fast. So boom, boom, bada bing, bada boom, things go fast, probably electricity. The other school of thought was the chemical neurotransmitter hypothesis, which are just chemicals being sent from one nerve to another. The argument for this was certain meds that were known not to interfere with electrical activity can inhibit nerve function. For example, Curar blocked neuromuscular transmission, causing paralysis without preventing nerve potentials. You could continue to measure action potentials across a nerve even though the nerve was blocked. The argument against neurochemistry, being the de facto way nerves communicate, was that it takes time. How could it be possible that one nerve was developing and sending out a chemical communication in the synaptic gap between the nerves, and the next nerve was receiving that signal, binding to that receptors, and then creating a new signal within the nerve? The debate between the two was called the soups versus the sparks. It's kind of a fun name. And nobody can figure out how to prove it one way or another, until a middle-aged German physician who almost failed out of medical school and who wanted to be a painter had a dream. I know, people get a little uncomfortable when I mention early 20th century Germans who wanted to be painters but couldn't. But this guy's dream was incredible and actually changed our understanding of human physiology and medicine. Now let's start with that dream, okay? 1921. Here is a very famous part of his diary that he wrote. The night before Easter Sunday, I awake, turned on the light, and jotted down a few notes on a tiny slip of thin paper. So he's obviously woken from sleep. Then I fell asleep again. It occurred to me at 6 in the morning that during the night I had written down something important, but I was unable to decipher the scrawl. The next night at 3 o'clock, the idea returned. It was the design of an experiment to determine whether or not the hypothesis of chemical transmission that I had uttered before was correct. I got up immediately, went to the laboratory, and performed a simple experiment on a frog heart according to the nocturnal design. So if you didn't catch that, he was sleeping, he woke up from the middle of a dream and jotted down this experiment that he had dreamed of. And then he fell back asleep, and then he woke up again the next morning and couldn't read his handwriting. There's a Seinfeld episode about this, by the way.
I got up last night, I wrote this down, I thought I had this great bit. Wait a second. Fax me some halibut.
And he's like freaking out, like, oh my God, I had this great experiment in my life. I don't remember what the experiment was about. And like, I lost it. I couldn't remember what it was, and I can't read my handwriting. So luckily, he went to bed the next night, and he woke up again with the same dream. And at this time, he didn't just sit down. He ran and actually performed the experiment. Before I tell you what that experiment showed or how it was performed, it's actually really simple. It's really amazingly simple, and there were profound implications of that experiment. I'm going to kind of talk you through what some of the plants that were used at that time to treat asthma, and then we'll come back to discuss the experiment. I want to go back all the way to 1802, where a letter from a British physician describing a plant that he unexpectedly came upon in India that was helping people breathe. You see, the British were in India in the early 19th century doing, things the British did.
Just added India to the collection.
Oh, splendid. A few more and you'll complete South Asia.
I've been eyeing Burma for months now.
Yes, it would look lovely beside India.
And in India, this botanical discovery bore various titles. It named many things, including thornapple and the devil's trumpet, which is a pretty fun name, and it is later called Jimsonweed. So This is now a diary entry from this same physician who was in India. I received from General Gent a remedy that he had not long before brought from Madras, which is southern India, now called Chennai, which the general informed me was used there as a specific for relieving the paroxysms of asthma, and that is prepared from the roots of the wild purple-flowered thornapple. The roots had been cut into slips as soon as gathered, dried in the shade, and then beat into fibers resembling coarse hemp. The mode of taking it in was via smoking. It was smoked in a pipe at the time of the paroxysm, either by itself or mixed with tobacco. So this was a common and recurrent theme in early asthma treatment, as lots of times people were basically grinding up various herbs and then smoking it, which you can kind of imagine why that was done, because you're imagining you're trying to get everything into the lungs, so smoking it was thought to be the most direct way to do it. And we know now that smoking, especially tobacco, can irritate the lungs and trigger asthma exacerbations, but back then we didn't know quite as much. Before it was totally recognized as being helpful for breathing, before the 1800s, it actually had a more sinister reputation. In 1676, in Jamestown, Virginia, British soldiers were sent over to quell a rebellion, and the British soldiers rounded up plants to make a salad to survive and eat in the forest around Virginia. And they apparently boiled some what is now called Jimsonweed, or also the devil's trumpet. In a book from 1705 about the history of Virginia, the authors outlined the soldiers, quote-unquote, presented a very pleasant comedy, for they turned natural fools for many days. One would blow a feather in the air, another would dart straws at it with much fury. Picture that in your head. And another stark naked, sitting up in a corner like a monkey. I can visualize that one. And the soldiers continued to exhibit this very unusual behavior for 11 days, reportedly. So after eating this toxic plant, and then once again, it had multiple names at that point, but it was henceforth named in the colonies after the town where this occurred as Jamestown weed. And over time, that term just became Jimsonweed. So apparently, depending on the amount and how the plant was consumed, it could have very different effects. But one thing is they don't put it in a salad, okay? So this is sort of an interesting little historical anecdote that these people got pretty poisoned, people even dying from ingesting too much of this weed, having very severe altered mental status, having very severe tachycardia, very, very high heart rate. Fast forward a century, and it has started being used for asthma treatment. And in fact, according to Dr. Hyde Salter, the prominent physician featured heavily in the first episode, known as the quote-unquote asthma guru, Jimsonweed proved to be more effective at a prevention than a cure. Indeed, he advocated smoking a pipe each night before bed in order to keep the disease at bay. The Jimsonweed seems to leave for some hours a state of nervous system in which the asthma is not likely to come on. And since the attack is almost always at night, the use of Jimsonweed at bedtime conducts and guards the patient through the critical time. So the idea is to kind of prevent it by proactively smoking this plant prior to sleeping. We now know preparations of this plant were utilized mostly through grinding it up and smoking it, as was most treatment of asthma in the 19th century. But even back in the day, people would complain of hallucinations, blurred vision, tachycardia, again the high heart rate, constipation, and changes in mental status. So it wasn't without its side effects, but again, this was the 1800s and there wasn't a whole lot of other options. Next plant I want to talk about is Atropa belladonna. The plant very well documented to be used for centuries and centuries prior to the 19th century. It's called belladonna because it was ground up and put with water and then used as drops. So these women would put droplets into their eye. It would actually make their pupil dilate, expanding the dark of the eye, and that made them feel more beautiful, which is why it's called belladonna, which is beautiful woman, a phrase in Italian. Then we get back to Dr. Hyde Salter in 1869. He says, quote unquote, "I do not know of any sedative that has more improved its position of late than belladonna. I went on so long without giving belladonna a fair and thorough trial in asthma. The last 2 years, however, I have used it extensively, and am so satisfied with the result that I think it's worthwhile to publish." He goes on to describe a few cases. A 25-year-old woman couldn't sleep for the last 1 month because of episodes of shortness of breath kept her awake. She was prescribed 10 minimums of a tincture of belladonna 3 times a day. She felt great after 9 days of taking it, so she stopped. She said, "I have no more symptoms of my asthma." So she felt confident that she was cured and she stopped it, but unfortunately the symptoms came right back and she had to stay on it. The authors go on to describe 5 more patients that had dramatic recovery while taking the belladonna. But I was more interested in what the heck is a minimum of a tincture. So back really quickly, I said that she had 10 minimums of a tincture of belladonna 3 times a day. Like, what? I've done a lot of medical history, have not come across 10 minimums of a tincture, what on earth that means. So they inhale it, they swallow it, what's going on? It turns out they swallowed it, and it's a very apothecarian term. It was Latin for the smallest amount, which sounds about right. Before this term, this is sort of an interesting background of why we had tinctures and minimums, was the smallest dose was a drop. But in the 1800s, something important happened. Scientists were able to start isolating various chemicals, and they recognized that some chemicals have different viscosities. So a drop of one chemical is a different amount than a drop of another chemical because of the viscosity in the droplet would form differently if the viscosity is different. So they realized they needed a better way to have more consistency in their measurements. So the League of Apothecaries, actually I made that up, I'm not sure what the governing body of apothecaries was at the time. They got together and standardized that the smallest unit was defined as a single drop. A drop was closest to 1/60th of a dram. And what is the dram? This keeps going on, right? It's a small glassware to measure volume. So it's a small glassware, and they actually were able to make pipettes that was 1/60th of a dram. That was apparently a much more consistent way of measuring the smallest amount compared to a drop. I get a little beside myself here. Sorry. So back to belladonna. So people smoked it for asthma as well. And lo and behold, it also had similar side effects to Jimsonweed. Dry mouth, tachycardia, constipation, changes in mental status, and that blurred vision, probably because the pupils dilate, letting more light in, and it gets overwhelming. So you can see an overlap between the benefits of Jimsonweed and the benefits of belladonna. And you also see an overlap of the side effects of Jimsonweed and the side effects of belladonna, both being used to treat asthma. A next big leap occurred in 1831. A German physician actually isolated the common chemical. He was able to crystallize it from both Jimsonweed and belladonna. And he called it atropine because it came from Atropa belladonna, the plant. And also, atropos is one of the three fates in Greek mythology responsible for cutting the thread of life, referring to its toxicity. And he was able to isolate what was in those leaves that actually triggered the side effects, but also triggered the ability to breathe better, helping to open up the airways. So the interesting thing is, once they're able to isolate atropine, they're actually able to measure it in the leaves. And this is important because it actually gave an explanation for why some people would smoke the leaf of either Jimsonweed or belladonna and have severe side effects, have the mental status changes, the tachycardia, and the constipation, while other people just feel like they could breathe a little bit easier. It's because they realized from leaf to leaf, the amounts of atropine varied greatly, and they were unpredictable. So some leaves had more atropine, and the other leaves had less atropine. So you had a bit of a roll of the dice whenever you smoked it on how much atropine was there. Hopefully it's just enough to open those airways and not cause much problem, or it had a whole lot of it and you were dancing around naked like a monkey, as was said. So this is a mechanism of action podcast. Let's talk about how atropine caused these lists of side effects. And how do we figure that out? Well, before we get to that, we first have to talk a little bit about the nervous system, a little bit of background about the vagus nerve and how atropine is impacting the nervous system in a way that helps explain the benefits from a lung standpoint, but also the bad side effects like tachycardia, constipation, and changes in mental status. So I want to talk a little bit about the basics of the nervous systems. This is a whole other history, and it's also a very interesting history, but we can't get into that. That would take like hours and hours to go through the history of how the nervous system was discovered, right? So we have, basics of what's called the autonomic nervous system, the part of the nervous system that we don't have to think about, that happens automatically, like having your heart rate going up to tachycardia. You don't typically consciously have to manage your breathing. If you're sitting still, you can get urges to have bowel movements back and forth. You have automatic changes in your body when you don't tell your body what to do. That's part of the autonomic nervous system. So it turns out there are two major components of the autonomic nervous system. There's the sympathetic nervous system and the parasympathetic nervous system. The sympathetic is the fight or flight component of the nervous system, responsible for immediately fleeing a lion. If you come across it, for example, it gets the heart rate up, it dilates the pupils so you can see more, it helps open up the airways so you can breathe in more while you're running away from the scary big lion, and helps decrease and actually stops or halt digestion. In contrast, we have the parasympathetic nervous system, the rest and digest aspect of the nervous system. So this is exactly the moment when everything's chilling out. You're in the cave, you got a fire going, you have some people around the cave entrance so you feel guarded and safe. Things look good in life. That's when you can call rest and digest. The digestive system, the intestines start waking up and your heart rate goes down. Your bronchioles actually constrict at this point, and also your pupils narrow. These two systems were slowly elucidated during the 19th centuries in various countries, but the experiments I'm going to focus on took place in Germany by two physician brothers named the Weber brothers. And they were interested in how this large nerve coming from the brainstem, which connected and transmitted signals to multiple organs, including the heart, the ocular system, the lungs, and the intestines, may be involved in the parasympathetic nervous system. And this nerve coming from the brainstem, this nerve was called the vagus nerve. It was actually on both sides of the neck, coming away from the brainstem and then kind of hooking up to multiple organs along the pathway. So they did some experiments to try and prove what the vagus nerve was doing. They actually cut open a frog's chest. A frog is a recurrent sacrificed animal, by the way, in this whole story. So they cut open a frog's chest, cut the pericardium while alive, so the heart was beating, okay? And then actually slice into the neck of the frog. And from the incision, they would find and isolate the vagus nerve. Then using an electromagnetic apparatus, they applied strong electrical stimuli to the vagus nerve and recorded changes in the heart. And lo and behold, the heart rate slowed. And they established the role of the vagus nerve was parasympathetic activation along multiple organ systems. The heart caused slowing of the heart, i.e. bradycardia. The lungs actually cause bronchoconstriction or narrowing of the bronchioles. This activation caused vasodilation and decreasing of the blood pressure. So they recognized that the vagal nerve is having effects on multiple different organ systems, and it seemed to be the driver of the parasympathetic nervous system. Okay? But now we get back to that age-old question, the soups versus the sparks. The next question was, how was the vagus nerve communicating with the organs? How were these nerves communicating? Was it electricity or was it chemistry? Okay. Now we're going back to Dr. Loewi and returning to our story about the German doctor. After his dream, he woke up with a fright and ran and got the frogs. Remember lightning, thunder. Okay. And he went and killed frogs, cut out their hearts, and put them into jars of saline while they were still beating, and then performed a relatively simple test. So take a step back real fast. This guy apparently woke up in the middle of the night, like 3 a.m, and went and killed frogs and did this experiment. So were the frogs in his house, or did he leave and go to the university? I don't know the answer to that. So all I could find was he went and did these experiments in the middle of the night. Back to the frogs, their hearts were removed and isolated, and they continued beating. So it was a critical aspect of the story. The hearts kept beating for a while. And I didn't really know this was a thing. So yes, apparently frog hearts continue beating because the pacemaker is in the heart itself and is entirely independent of the brain. If the heart is placed in an oxygenated water bath, the heart remains functioning and it can continue beating for hours. So who knew? Okay, so that's out of the way. We got the answer to one of these fascinating conundrums. So Dr. Loewi placed 2 isolated beating frog hearts, each in its own perfusion chamber. And this perfusion chamber had saline around it, okay? One heart had the vagus nerve still intact and connected to it, while the other was denervated, so I completely had the vagus nerve cut. So next, he stimulated the vagus nerve with the device I previously mentioned, and lo and behold, the heart rate, I'm making up a number, was like 100, and it went down to 50. So this was not new. Remember, the Weber brothers from Germany had done the same experiment, so he already knew that was going to happen. But this is a stroke of genius. It's very simple, really. So he was trying to prove, was it electricity or was it a chemical causing that transmission? So what did he do? He took saline from the chamber with the slowed heart, and he just moved it with a pipette and squirted it into the other chamber with the other heart that had no vagus nerve. And lo and behold, that heart went from 100 beats a minute down to 70 or 60. So that heart decreased. This was clearly showing some chemical messenger was being released from the vagal nerve. So this is a huge deal for physiology. It's clearly showing some chemical was being released by the vagus nerve to slow down the heart. He named the inhibitor Vagusstoff, which is a great name, but scientists did not want to use such a fun and exciting word, and they turned it down and switched the word eventually to acetylcholine. Ooh. So how does this help us? Remember, the whole point of this episode was kind of focusing on these early asthma medications, primarily Jimsonweed and belladonna. And remember, asthma is bronchial constriction, which is what the parasympathetic nervous system does. And we just learned that parasympathetic nervous system was triggered by the vagal nerve, and it was released by Vagusstoff, aka acetylcholine. So it wouldn't be such a surprise that maybe whatever it was in plants, which we know is atropine, could be inhibiting the actions of the parasympathetic nervous system. We have enough knowledge now to be able to do an experiment to prove that. So we actually can just use atropine and then see if it will inhibit the vagus nerve and see what impact it had. And now we have the entry of Dr. Henry Dale. This is exactly what he did. Dr. Henry Dale is a British pharmacologist He has a lot of accolades to his name, including winning the Nobel Prize, another Nobel Prize winner. He was lifelong friends with none other than Dr. Otto Loewi, the German who originally wanted to be a painter, but ended up winning a Nobel Prize and changing our understanding of the nervous system. He also knew Paul Ehrlich, who was a huge name in immunology. He was the president of the Royal Society and the Royal Society of Medicine, and he was knighted. He had the Medal of Freedom. And he married his first cousin. I had no idea about this, but it was actually one of the last sentences on the nobelprize.org webpage when I was reading. It says all of his accolades and then says, oh, and he married Ellen Harriet Hallett, his first cousin, in 1904. So nobelprize.org is such a gossip mill, am I right? So Henry Dale, so he's the one who did this experiment. So he had made that same setup, right? He had the vagal nerve, the heart, and wanted to see what would happen. And he did successfully demonstrate that when exposed to atropine, it selectively blocked the vagal stimulation. And indeed, the bronchioles did not constrict, okay? In fact, it led to bronchodilation. And the same thing happened to the heart, where it blocked the bradycardia and it caused tachycardia. So the heart rate actually went up. So everything the opposite of what the vagal nerve was doing would happen when the vagal nerve is exposed to atropine, which is the substance inside Jimsonweed and inside Atropa belladonna. So this category of medication was called anticholinergic, which is a component of the asthma treatment, which was huge for much of the 19th and 20th century. These compounds were put into tobacco products and patients with asthma smoked them. In the 1927 edition of Cecil's A Textbook of Medicine, the author Dr. Francis Rackemann suggested smoking Jimson leaves, atropine, and belladonna as a therapeutic for asthma. This was brought up again in the 1947 edition of the book, and apparently 1975 was the year we finally saw when belladonna was officially kind of fallen out of favor for the use of asthma. The problem with atropine by itself is when you inhale it, it's very easy for it to get directly absorbed by the blood in the lungs, leading to this long list of symptoms such as tachycardia, dry mouth, constipation, and vision changes and potential mental status changes. Okay, so the problem with it was not only that you can't control the atropine, but also the problem that atropine itself was easily absorbed in the blood system. So in the 1970s, a renewed interest in anticholinergics took hold of the world of asthma, and less toxic versions of atropine were developed. Basically, the main target was to have critically less absorption in the bloodstream. So when these better drugs were inhaled, they would try and sit just within the lungs and not result in it being absorbed in circulation and cause that kind of myriad of anticholinergic side effects. And this led to the development of short and long-acting anticholinergics. For example, ipratropium and tiotropium, which have various pharmacodynamics and pharmacokinetics, each creating unique absorption changes. This is the story kind of to appreciate some of the fascinating history of early medications, early therapeutics used for treating asthma far back in the 19th century. At least in the Western world, they were being used even earlier than that in India, for example. And we recognize that smoking was kind of the most common way to take this, but we clearly recognize that they had a lot of side effects from them, and the major connection after isolating atropine from both these leaves, but really critically was the German physician's experiment that demonstrated a really simple experiment when you think about it, and clearly demonstrating that a chemical is being released from the vagus nerve, and it caused the bradycardia and the other side effects of treatment. And it's pretty wild. I mean, it happened from the same guy having the same dream twice in a row, and he couldn't read his handwriting in the first one. It's a great story. So in conclusion, I hope you appreciate the journey we took on how anticholinergics were discovered and their major impact on the treatment of asthma when very little else was offered, and really kind of changed people's lives around. In the next episode, we're going to dig into the many individual classes of asthma medications and their unique mechanisms of action that are used to treat asthma in the more modern era. So I hope you learned something. Hope you enjoyed it. If you did, don't forget to please tell your friends about us. Please give us a 5-star review. We're a new podcast and trying to grow. Thanks again.